And so when I started, it was mainly people connected to universities. And so it was very fun talking about physics to grads. It would be like, I don't think undergrads typically had an internet account back then. So it would be like grad students and professors. But unfortunately, the internet caught on in popularity. And so more and more people got involved. And so what happened was people started learning about these physics and math discussion groups. And some of them were non-experts who were really great people, really interesting people who, normal, normal people who would like have lots of questions and things like that. And that's fun. That's part of how I got into explaining so much math and physics. I got really a lot of practice explaining all sorts of stuff. Um, but there are a lot of people out there, not as many as ordinary people, but there are a lot of people who come up with their own theories of physics and sometimes their own supposed proofs of solving famous math problems. And when they discovered that there was a way for them to communicate with experts around the whole world, they got really excited and they started telling us their crazy theories.
The guest of today's podcast is Dr. John Baez. He is a theoretical physicist and mathematician, previously at UC Riverside and now at University of Edinburgh. He works on quantum gravity, network theory, and higher categories, among other things. So let's talk to Dr. Baez about his work in physics and mathematics and listen to what he has to say. So, Dr. Baez, welcome to the podcast. It's nice to have you.
Thanks. It's great to be here.
So before we talk about anything else, can you tell us a bit about the project that you are working on nowadays?
Sure. Right now, my main work is with a team of people trying to develop software for modeling in epidemiology, although it may also apply to economics and other things. It's very flexible modeling software based on category theory in part. And so I'm working with a team that includes some computer scientists who specialize in epidemiology and some computer scientists at the place called the Topos Institute, which is an institute set up by a former student of mine, Brendan Fong, at Berkeley, that does research in category theory. And I'm mainly doing some of the math in part of this project. So that's a very nice practical project. And then I have enough leftover energy so far. I've just started my job in Edinburgh, so it may change, but so far I have enough leftover energy that I carry out research on various random topics of interest and trying to finish writing some books and things like that. So different topics in mathematical physics, mathematical music theory, abstract algebra, category theory, things like that.
What kind of topics will be included in the book on mathematical music theory?
It's very limited in scope. It's about different tuning systems. So
Mm-hmm.
before we got the equal tempered tuning systems where the distances between each note is the same in a certain logarithmic sense, in the West, various other tuning systems were used. And I'm just trying to cover the most popular Western tuning systems from different eras, starting from the Middle Ages. And they're mathematically very interesting. And each of the most popular ones was actually good for the kind of music that was being played at that time, which is, I find interesting.
You have done quite a lot of work on physics, but correct me if I'm wrong, but you're predominantly a mathematician, right? So how did you get interested into physics?
I was interested in physics before I was interested in mathematics. My uncle was a physicist. He was the father of this rather well-known folk singer, Joan Baez, but he worked for UNESCO, this United Nations science education program. And so he would come by my parents' house occasionally and always have interesting experiments to do physics education, like with things like lasers and so on. And he gave me a copy of his college physics textbook that he wrote when I was 8 years old, and I was fascinated by it because it had interesting pictures. So I decided at a very early age that I wanted to do physics, and I switched toward mathematics just because I became very frustrated in junior high school and high school that I was not able to do experiments with elementary particles or other exciting things like that. And so I learned that I could do mathematics just sitting at home, scribbling on paper, and that leaned me towards mathematics. And then by the time I went to college, I had to decide whether to major in mathematics or in physics. And I chose mathematics because there I could always understand exactly what the questions were asking. It was very clear and precise. By that time, that mattered a lot to me. And so physics, although I loved it, I found a little bit more slippery, hard to know what the question was exactly asking. So just for that practical reason, I went into mathematics. And I guess I'm glad I did, although I do a lot of both mathematics and physics. I feel very comfortable proving theorems, so I enjoy being in a mathematics department.
I see. So, one of the topics that you have worked on quite extensively is the topic of Octonions. And I remember that when I was trying to learn about the G2 group, I
Uh,
read your writings on Octonions, on your website. So, can you tell us a bit about, so correct me if I'm wrong, so, the work that you did on Octonions had, this part where you try to link it to applications in quantum logic and special relativity as well. So, can you tell us a bit about what Octonions are and why were you interested in Octonions?
sure. I heard about the Octonians from some people who seemed very strange, and so they didn't initially appeal to me. But I learned this theorem that says, so if you have a, I hope I'm allowed to stop me if I start sounding demathematical, but so so if you have a finite dimensional algebra, so that's a finite dimensional real, let's say, vector space with a multiplication, may not be associative, um, but it has an identity element, so there's an identity for the multiplication. So you should be thinking something like the real numbers or the complex numbers so far. And then we want it to have a norm, so some kind of absolute value operation. I guess I won't specify the axioms it needs to obey, but one axiom that's very unusual that we want it to obey is that the norm of x times y is equal to the norm of x times the norm of y. So like if you think of like the absolute value of a real or complex number, the absolute value of x times y is equal to the absolute value of x times the absolute value of y. And that's a very powerful axiom. It means that it means that if you multiply two things that aren't zero, the result can't be zero because one of the axioms of the absolute value is that the only thing whose absolute value is zero is zero. I didn't list all the axioms. So this kind of, I sketched it out. This kind of gadget's called a norm to division algebra. And then there's this amazing theorem that I heard about, which says that there are only four norm division algebras. There's the real numbers, which is a one-dimensional vector space, like a line. There's the complex numbers, which is two-dimensional vector space. You have a complex plane. There's the quaternions, which are a four-dimensional vector space. Those are much less well studied. You don't always learn about the quaternions if you go to get an undergraduate degree in mathematics or physics. But they're very, very nice. They're not commutative. The commutative law fails for quaternions. You have these quaternions called 1, I, J, and K, and then real linear combinations of those. And they obey rules like I times J is equal to K, and which should remind you of like the cross product of I and J is K, if you think of those as basis vectors in 3 dimensions. They were invented, or I should maybe say discovered by by Hamilton. So they're not commutative, but they are associative. The associative law that x times y parentheses times z is equal to x times parentheses y times z. That law still holds for the quaternions. And then when Hamilton invented the quaternions, he wrote a letter about them to his friend, John Graves, who was a lawyer, who was like a college friend of his. And his friend started thinking about it for a while. And he wrote a letter back saying, oh, I invented an 8-dimensional norm division algebra. And he had, and that's called now the Octonions. And that's the last one. And that one is not even associative anymore. And so when I heard about this, it just struck me as extremely strange. It's very weird that you have this mathematical concept. It seems like a reasonable concept, norm to division algebra, and there are just 4 of them. The first 2 we use all the time in math and physics. They're like super important. The third one, the quaternions, we don't use very much, but Hamilton actually was very excited about them. And they were invented before anybody had developed the cross product of 3-dimensional vectors or the dot product. And they actually contain the dot product and the cross product in their multiplication, both aspects. The real part of the multiplication is minus the dot product. The imaginary part of the multiplication is basically the cross product. And so he got really excited about them in the late 1800s, or actually the early 1800s. And so for a long time, people were using quaternions to study physics, and then only later did Gibbs, the first, he's a famous physicist, but he was also the first math PhD, I think. I think it was a math PhD, maybe it was a physics PhD, and first one in the United States, actually. He split the quaternions into the real numbers, which we now call the scalars, and the other 3 dimensions, which we now call vectors. And he split the quaternion multiplication into the things that we're familiar with: the dot product, the cross product, and the multiplication of a vector by a scalar. And that became very popular, and there was a war between the quaternion fans and the vector fans, and the vectors won, obviously, because that's what we learn now. So what I'm trying to say here in a very long-winded way, because it's a really fun subject, is that once upon a time, the quaternions were considered very important in physics. Then they were sort of hidden by being broken apart. Then they were sort of reinvented when Pauli invented the Pauli matrices in quantum mechanics. Those are similar to the quaternions. So they're important, but they're just sort of hidden, let's say. But the Octonions are much more mysterious than that. There's no really obvious application of them to physics. When I mean obvious, so there's not like a bunch of physics problems where you suddenly need Octonions. And so I became fascinated by them, and I gradually learned. I did a lot of research that was just like learning what other people had done, because it tended to be scattered around all over the place. And so my article on the Octonions was mainly an attempt to gather a lot of information and present it clearly. But then I wrote a couple of papers with my student John Huerta about how the Octonions show up in string theory and also 10-dimensional supergravity and 11-dimensional supergravity. And by the time we were done writing those papers, it was very clear to us that a lot of what's special about string theory is connected to the Octonions. So I'm not a big fan of string theory, but if I were, I would say that, like, okay, this is for superstring theory. I should emphasize that if I were, I would say that, okay, so this 4th number system is sort of waiting there for string theory to become realized as a true theory of physics, and then we will see the significance of this 4th norm division algebra. Mm-hmm. So I find it very fascinating, and I don't feel the need to believe in superstring theory to to have found it very interesting to. I basically learned what some string theorists were already saying about how the Octonions are connected to superstring theory. But in my papers with John Fairder, we tried to clarify that, explain it more mathematically, and also connect it to what we call, well, what a bunch of people call higher gauge theory, which is a generalization of gauge theory that is good for studying not just point particles, but higher dimensional things like strings and branes. And so there's this very nice mathematics connected to the Octonions and higher gauge theory. Um, so yeah, so that kept me interested for quite a while.
Right. But in your article, you also mentioned that Octonions are also, also have applications in quantum logic. What kind of
That's
applications
true.
are
Calling
they?
them applications is a little bit of a
Mm-hmm.
stretch,
Mm-hmm.
but nonetheless, so in quantum logic, there are many approaches to quantum logic, but one. So I'm trying to hesitate and think a little bit here, but one approach to it's not the most logic flavored approach, but well, sorry, I guess you could call it quantum logic. So there's an approach to quantum mechanics where you think of propositions. In the simplest example are like subspaces of a Hilbert space. So if you want to say like, I've got a box of gas and the energy of the gas is, we know for sure that the energy is over five joules. So we're in some subspace of the Hilbert space where where you only care about eigenstates where the energy is bigger than some number. So we have a subspace, and then you can talk about the projection operator onto that subspace of the Hilbert space. And you can think of that either the subspace or the projection operator as being a proposition in quantum mechanics, namely that it's a way of saying like we know something is true about the system, in this case like that its energy for sure is over 5 joules. And so the interesting thing about these propositions is that you can develop a kind of logic for them with operations like and or, but it differs from classical logic because and does not distribute over or as it does in classical logic. And so now when you try to classify possible quantum logics, you can make up axioms for what you want quantum logics to be like. And Jordan, von Neumann, and Wigner came up with a very nice approach. And it led to this concept of a Jordan algebra, which is a kind of algebra of observables, and it contains certain observables that act like projection operators, but they would be propositions. And they classified the nice Jordan algebras that were finite dimensional, the so-called Euclidean Jordan algebras. And they discovered that you get a bunch coming from complex Hilbert spaces. Each finite dimensional complex Hilbert space gives you a Jordan algebra. So yay, those are the ones we learn about when we're studying quantum mechanics. To some extent, we don't call them Jordan algebras, but we work with that stuff. But then there's also an infinite series coming from real Hilbert spaces. So you can do quantum mechanics with real Hilbert spaces. People don't tend to talk about that so much, but you can do it. It's very interesting to see what's different about it. And you can do them with quaternionic Hilbert spaces. So there's an infinite series of quantum logics there. There's another weird infinite series called spin factors, which I don't think I'll talk about right now. And then there's one more, which comes from the Octonions. And it consists of 3 by 3 self-adjoint Octonian matrices. So observables in quantum mechanics come from self-adjoint operators, and so normally you talk about like complex self-adjoint matrices. But you could do real self-adjoint matrices or quaternionic self-adjoint matrices. But for Octonions, it doesn't work above dimension 3. the lower dimensions are already covered by the other examples that I mentioned in some interesting way, but the three Octonian matrices give you a thing called the exceptional Jordan algebra. And that's this weird possible quantum logic that people have often wondered, is it good for anything? So calling it an application is sort of, I guess you could call it an application. But I mean, it would be a real application if you found some physical system whose logic was described by this exceptional Jordan algebra. When it was first discovered, because it involves 3 by 3 matrices of octonians, people thought, oh, maybe it's connected to the color degrees of freedom of a quark somehow, just like 3 colors of a quark, just because of the number 3, basically. And I don't think that really works very well. People tried it, and it doesn't really work very well. So no one really knows quite what it does. I've written about some work by these fellows, Dubois, Violette, and Todorov, who've shown that there's a beautiful connection between the standard model gauge group and the exceptional Jordan algebra. So that's an attempt that people have been making to try to say that the standard model is connected to the exceptional Jordan algebra. That would be great, right? I mean, that would be the kind of thing that you would hope to do. There are problems with that idea, so I don't say that we have succeeded in applying the exceptional Jordan algebra to physics yet, but that's one attempt there.
I see. So another topic that you have worked on is knot theory, right? And there are relations that people talk about, which are between knot theory in 3 dimensions and quantum gravity in 4 dimensions. So can you tell us a bit about what knot theory is and what is this relationship between quantum gravity and knot theory?
Sure. So knot theory is the study of knots. It's the study of all the things you can form by taking a piece of rope, tying it up however you like, and then gluing the 2 ends together, attaching the 2 ends so that you can no longer untie it. And so then what you have is a loop of rope stuck into 3-dimensional space in a complicated way. So mathematically, we abstract that by saying it's an embedding of the circle in 3-dimensional space that cannot be deformed to the usual circle called the unknot without, well, the knot either crossing itself or maybe shrinking the knot down to nothing and expanding it back out or some cheating kind of way like that. So, and so there are, you can ask, given 2 knots, can you get from one to the other by wiggling around the rope without doing any of these cheating kind of tricks like having it cross over itself? And it turns out that there's many different kinds of knots that cannot be transformed into each other by these valid maneuvers, which are called isotopies. And there's a countable number of them. And Kelvin, the physicist Kelvin, got interested in them in the late 1800s because at that time people believed that the ether, the material that carries the propagation of light, might actually be a fluid. And Helmholtz noticed that an ideal fluid can have vortices flowing in it that will never dissipate. There's a certain kind of conservation of vorticity in the motion of an ideal frictionless, incompressible fluid. And Helmholtz did things like experiments where you like blow a smoke ring and see the smoke ring go through space. And then if you shoot 2 smoke rings at each other, they can like go past through each other but continue on. And so Helmholtz and I guess, but mainly Kelvin came up with the idea that maybe atoms are knots in the flow of vortices in the ether, because that would account for the fact that we have this sort of discrete set of possible atoms, which was very strange, given that the theories of physics at the time were all sort of continuum theories, continuum PDE. How can you get a discrete set of entities out of that. So that theory didn't work, but and then people came up with quantum mechanics, which is the right answer to that puzzle. But Kelvin got his friend Tate, who actually lived here in Edinburgh, to try to classify knots to see if there's any relationship between the classification of knots and the periodic table. Well, there's not any. You can classify knots, and it doesn't look at all like the periodic table. There's not like halogens and rare earth metals or anything like that in the knot theory. But people started getting interested in classification of knots because mathematicians are interested in everything, and so people slowly studied that. And then much more recently, in the 1980s, it was discovered that there were some ways to compute invariants of knots, compute numbers from knots that could help you classify them using quantum field theory in 3 dimensions, using a certain quantum field theory called Chern-Simons theory. It's a long story, but Ed Witten wrote a very important paper called something like the Jones polynomial and Chern-Simons theory. I don't think that's the exact title. Yeah, and he showed that certain observables in Chern-Simons theory give knot invariants, which had recently been discovered by von Jones, connected to some mathematical structures called quantum groups, or for von Jones, certain von Neumann algebras. So there's some really interesting mathematics there. And then people noticed that certain approaches to trying to quantize 3+1 dimensional gravity, that is like actual, well, more close to actual quantum gravity, still with no matter, just gravity, seem to say that there should be a state of quantum gravity connected to Chern-Simons theory. One state, and this state should, if you measure certain observables in this state, it should give you knot invariance. The same knot invariance called the Jones polynomial. Same knot invariant called the Jones polynomial. And then people started trying to connect knot theory in more detail to 3+1 dimensional gravity using an approach called the Ashtekar variables, or new variables for quantum gravity. And so I was interested in working on that. And I mean, the short answer I'd say is I don't think that stuff really works very well. It would be nice if different knot invariants would correspond to different states of 3+1 dimensional quantum gravity, because knot invariants are something you can mathematically study, and they are diffeomorphism invariant quantities that don't change when you apply a coordinate change to space, and you would like states of quantum gravity to be diffeomorphism invariant in that respect. But no one has really gotten everything to work. I mean, that's the short answer, and that's why you don't hear about this very much these days. I mean, people will argue with me as whenever you say anything doesn't work in physics, there will be physicists who say, no, we're still trying to get it to work. So you never know for sure if something doesn't work until the universe ends, I guess.
I see. So you mentioned that it would be nice if different knot invariants corresponded to different states in quantum gravity. So what other knot invariants do we have apart from Jones polynomial?
Well, there are lots of invariants. The closest thing to kind of a systematic collection of invariants are things called Vasiliev invariants. So it turns out that you can do Chern-Simons theory with any gauge group, any compact Lie group gives you a version of Chern-Simons theory. And thus it gives any one of those Chern-Simons theories with different gauge groups gives you a knot invariant of which the Jones polynomial is the one one of the simplest. The one comes from the group SU2. And when you take these different non-invariants and you expand them perturbatively in the coupling constant of the theory, the terms in the perturbative expansion are called Vasiliev invariants. And you can define Vasiliev invariants in a way that doesn't involve Chern-Simons theory. So you can just talk about Vasiliev invariants. And then you can show that a bunch of them come from Chern-Simons theory. But I think, so there's a big mathematical question of like, do they all come from Chern-Simons theory or not? I haven't even kept paying attention recently on that issue. But you could hope, for example, that all these Vasiliev invariants gave you states of quantum gravity, because that would be nice, just because that would be like some mathematically tractable structure that you could use to try to gain information about quantum gravity.
I see. So another, topic, I think it's one of the most important topics that I want to talk about today that you have worked on is the topic of categories and higher categories, right? So you had this paper, called categorification with, James Dolan, in which you, talked about this program of replacing set theoretic, concepts with, category-based concepts. And so that program also inspired this, discovery of the classification of topological field theories by Jacob Lurie. So can you tell us a bit about, what categories are, what higher categories are, and what this program that you, wrote about, and, the called categorification is?
Uh-huh. Sure, that's a huge question. I should say that this is the thing I did that was actually successful, unlike some of the previous things you've mentioned. So that means there's a lot more to say about it. And it's successful not because of what I did, but it's because like what dozens or maybe even 100 people have been doing. So it's very hard to summarize, but nonetheless, I'll do it anyway. So a category is a little bit more fancy than a set. So a set is just a bunch of things. And when you try to draw a picture of a set on a blackboard, typically what you draw is a bunch of dots and a little bag around them, so you know which dots are in the set and which are out of the set. So that's a perfectly good image. That's not a mathematically rigorous approach to set theory, but that's what you should have in mind when you're thinking of a set. Now, with a category, the idea is that besides those dots, we will also have some arrows, and an arrow will always go from one dot to another dot. And these arrows have some extra abilities. If I have an arrow from X to Y and an arrow from Y to Z, there's a rule that says that I can compose them or multiply them to get an arrow all the way from X to Z. And that composition needs to obey the associative law. And also, this is the end of the definition, is that every object has an identity arrow that goes from that object to itself. When you compose with an identity, it doesn't do anything. It's just like one, like multiplying by the number one. So basically, we've taken this concept of a set, which is somehow static. You just have these things sitting there, and made it more dynamic, because now you have things, but also these arrows, which are abstract ways to go from something to something else. And so it makes for a much more lively concept. Now, there are millions of examples of categories. And category theory is the realization that whenever you study a subject in mathematics, like group theory, linear algebra, topology, graph theory, et cetera, whenever you study a subject, you are studying one or more categories. So for example, there's a category of vector spaces where the objects, that's what we call these dots, where the objects are vector spaces. And I have to imagine a huge thing where each dot is a vector space, and they're all the vector spaces in the universe there. And then the arrows between them are called linear maps or operators or whatever you want to call them. So there's a thing about a linear operator between, it has lots of names, linear operator, linear transformation, linear map from one vector space to another. And then you can compose those. When we first learn about linear operators, they tell us they're matrices. And composing those is called matrix multiplication. Then later on, when we get more abstract, we think about them in other ways. You should just think of, if you want, you can think of them as matrices. And in quantum mechanics, we become very excited about that because we say, oh, I can use my vector spaces, maybe make them a little fancier and call them Hilbert spaces, have a little bit extra stuff going on there, to describe the possible states of a quantum system. And then observables would be certain linear operators, or transformations that describe how things evolve in time would be linear operators. So quantum mechanics, you could say, is this like the study of a certain category of like Hilbert spaces, which are like jazzed up vector spaces, and linear transformations between them. And that's just one category. But there, like I said, there's like a category of there's like a category of topological spaces, there's a category of graphs, as in graph theory, there's a category of sets, all of sets in the universe, and the functions between sets form a category. And so what you learn in category theory is that by learning category theory concepts, you can apply those concepts to many different topics in mathematics at once, because each different topic in mathematics is studying one or more categories. And so category theory sort of gives you mathematical superpowers, because it means that when you come across a new subject in mathematics, you don't treat it as just like, oh no, here's some completely new subject. You say like, oh, here's another category. Okay, let me ask properties of this category so I can fit it into my mental framework and see how it's the same or different than the ones I already know. So you can sort of survey different mathematical topics, just as if they're like different mathematical structures, just like they're different sets or different graphs or whatever, they're different topics in mathematics or different categories. So this started a whole new approach to mathematics, starting in 1945 when Eilenberg and MacLane invented categories, and it's been developing ever since. And it's a very unifying way to think about mathematics. And I should say that there are also lots of other kind of categories that are just easy to draw on a piece of paper that don't have zillions of objects. You might study a category that just has 5 objects, and that could be very interesting too. So you don't need to think of a category as like a huge, big, scary thing. You can just think of it as like, I got some dots, I got some arrows, I can compose the arrows, and I can play around with that. Then eventually people realized that you should apply category theory to itself. Maybe they realized this like in the 60s or 70s. So what do I mean by that? Well, there's a thing of all categories. You could say at first, you could say there's a category of all categories. So now you have to imagine a big fat category where the objects in it, these dots, are different categories, all the different categories in the world. And then it turns out that people study arrows that go between categories, and they're called functors. So category theory is itself a mathematical subject, and so there's a category for it, which is the category of categories. That's sort of self-referential, right? If you talk about the category of all categories, it sounds a little scary. And well, it is a little scary. There are different things to be scared about there. But one of the most interesting things is that it turns out that there's more to the category of all categories. It turns out that it's something more fancy than a category, because it turns out that in addition to having these dots and these arrows between them, it turns out that they're like 2-dimensional arrows going between the arrows. So if I had some more paper, I could draw this, but I'm just doing it by waving my hand. So you got to imagine like one arrow from here, like another arrow from here to here. But now you can imagine like a sheet or a two-dimensional surface going from that top arrow to the bottom arrow. That's like a meta arrow, an arrow, a two-dimensional thing. And they call that kind of thing a two-morphism or a two-arrow or something like that. So those in category theory, they call them categories, they call the arrows functors, and these call these two-dimensional things natural transformations. And it turns out that when you study category theory, you need those all the time. They're just all over the place.
What do you mean by dimension in this context?
Well, so far it's extremely abstract. It's just that I'm very minimal. I'm just drawing the objects as a dot, and that's a zero-dimensional entity. Mathematicians call a point zero-dimensional because it takes no numbers at all to say where you are on a point. We could call the arrows one-dimensional because we draw them like a one-dimensional curve. You shouldn't take it too literally. We're not drawing these pictures in space are not the real thing. It's just like you've got two objects and there's a process going from one to the other. But when you draw them, you draw it often on the page as a one-dimensional thing, a curve. It takes one number to say where you are along a curve. So don't take it too literally, but then it turns out to wind up becoming very important to take it literally also. And then when you talk about a meta arrow, an arrow going between two arrows, it's very natural to draw that as like a two-dimensional surface. But it just means it's the next level up when you start talking about arrows between arrows between arrows. It's a kind of concept of dimension, but it turns out that it turns out that that something very interesting happens. There's something called a two category of all categories. And a two category is a thing that has objects, arrows between objects, and then these two arrows going between arrows. And then it turns out that this process just keeps on going on. So this thing with objects, arrows, and two arrows, we call it a two category. So in the 80s, people started studying two categories, and it turns out that there are lots of those. They're very interesting. Very few people were studying them at the time, so people considered them to be very abstruse and abstract. But in the 1980s, people started realizing that two categories, first categories and then also two categories, play a very interesting role in physics, for example, in quantum field theory. And they realized that the sort of these abstract concepts of dimension that I've been just talking about actually have examples in which they are perfectly literal, actual concepts of dimension in physical theories. So you can have like a particle, and a particle can trace out a path, which is like a one-dimensional thing. But then a one-dimensional thing, if you think of it now as a string can move along in time and trace out a two-dimensional kind of path, which is now a surface. People call it a string world sheet. And so it turns out that, like, to understand strings, two categories can be used. I'm not saying you have to do it, but I like to do it. You can study the different kind of ways that you can stick together string world sheets to form larger string world sheets using a two category. And so people started realizing that. And then people realized that it doesn't stop at the number two. It goes on and on to higher dimensions. So by now, this is a big subject. There's a whole big subject of n categories where you keep on going to higher dimensions. And there's a whole big mathematical physics subject of how n categories can be used in studying quantum field theories in different dimensions, where basically quantum field theories in n-dimensional space-time have strong connections to n categories. And this earlier stuff I was talking about how knot theory is connected to quantum field theory in 3 dimensions, like Chern-Simons theory, that fits into this picture in a very nice, in a very nice way. And in a sense, my failed attempts to relate knot theory to quantum gravity sort of were what led me to get interested in this more successful subject of how physics in different dimensions is connected to n categories for different values of n. I think I'll stop here. I think it should be obvious that I'm saying things that are very vague and mysterious, and that's because getting into the technical details takes quite a while. It's a very rich and interesting subject. Let's put it that way.
Sure, but I will try to put in jargon explainers and graphics to, aid the, description that you're giving. So,
Sure.
before I go back to the question that I asked about categorification and, that whole program, there is one question that I just thought of. So, when people, were studying set theory and they use the definition that set is just a well-defined collection of objects, we know very well that things like Russell's paradox, had
Uh-huh.
problems with this simple, definition of sets, and then you had to
Right.
come up with the ZF axioms to, avoid those kind of problems. So you just talked about categories of all categories. So do we have those kind of problems in category theory as well?
Yes, the same problems show up there, and the same solutions apply. People by now have worked on this a lot more, and in particular, Grothendieck developed a nice approach to dealing with these issues. So there, you can add to the traditional axioms of set theory called ZF axioms. You can add an axiom called Grothendieck's axiom of universes, and it's an extra axiom. It's widely considered to be likely to be consistent with all the previous axioms. Nobody can, you can't prove that the ZF axioms are consistent if using ZF theory anyway, because of Gödel's theorem. But no one's found an inconsistency, so that's the best we can do. So you can anyway. You're luring me into the joys of logic here, but which is like a really different subject. But you can add these axioms saying there's a set of sets that's so big that all the usual operations we do in set theory keep us in that big set if we start with sets inside there. So for example, if I take the union of some sets that are in that huge set, it's still in there. If I take the set of functions from one to the other, it's still in there, blah, 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 blah. So this big set is called a universe. So it's not all the sets, because there's no set of all sets, but it's a set of a bunch of sets that's big enough for practical purposes that you can work in that so-called universe and never feel any need to leave that universe. The only reason why you might need to leave that universe is if you want to talk about something like the set of all sets. Well, so what you can do is you can talk about the set of all sets in that universe. Well, that's just this universe. That's what this universe is. This universe is a certain set. That's the set of all sets in it. Duh. I mean, so now the universe is not in itself. The universe is not a set in the universe. It's too basically it's too big to fit inside itself in a very rough size way. So so then you could say like, oh no, what if I want to start dealing with sets that are like that big? Like say I want to like to square that set or something like that, multiply, take its product with itself. Well, so growth in the exact axiom of universe says, don't worry, there's some larger universe, some second universe that contains that first universe and all the things you might build with it. So there's another, so there, good. So we can work in that larger universe. And basically, growth in Leaks axiom says that there's like an infinite sequence of larger and larger universes. That now, so what you can do is you can say, okay, I can talk about like the category of all small categories. The category is small if its set of objects and its set of arrows are in this first universe. So the category of all small categories is a well-defined thing, but it doesn't live in this first universe. It lives in the second universe because it's talking about all categories in the first universe. That just winds up to be would be leading you to a Russell-like paradox if that was in the first universe as well. So, but it's in the second universe. And so basically, you go up as many universes as you need to in whatever argument you're doing. And typically, you don't need to go up that many universes in any argument that we normally carry out, even in this fancy-ass mathematics. Now, you may think this is like insane, but the really cool thing is that people now are working on developing mathematics using doing it very rigorously using computers. They want to have computer-aided proofs where each step of the proof is like carried out in software so that we know damn for sure there's no hand waving. And there are a couple of software systems like Lean and Coq and others that I'm forgetting now, which allow you to carry out rigorous reasoning in set theory and category theory. And it turns out that the serious systems here all have ways of dealing with universes now. And so in these systems, they have to decide like how they're going to handle universes and how you're going to deal with various issues that are associated to universes. So it's just amazing to me that these questions about universes, which I heard about like when I was young and like studying, when I was in college, I was also interested in mathematical logic. So I like took some grad courses on set theory and I decided like, yeah, this stuff is too weird. I don't want to think about it. And it didn't seem practical enough, basically. And I don't mean to put it down. It's actually really cool, but it just seems like very remote from anything. I was interested in physics too, right? I didn't think this stuff would ever intersect anything I cared about. But it's really cool that like by now you can like type into Google like universe polymorphism in Coq. That's COQ, by the way. The French like the fact that that sounds like a dirty word in English. Or universe polymorphism in Lean, and you'll see that like people have arguments like, okay, what's the best way to deal with this stuff? So anyway, it's been worked out. Let's put it that way. But it's not trivial to work it out. We could talk for too long about this. It's not one of
Sure.
my main interests, but nonetheless, yeah, it's a serious thing that you have to confront if you really, really want to get serious about this stuff. It's not very important as far as I'm concerned. Actually, you can just hand wave most of the time. But if you want to get it serious, like you want to write your proofs in a computer or something like that, then you have to learn this stuff.
So, as I mentioned before, that you had this paper with Dolan on, categorification, and, following that program, there was this paper by Lurie that, classified topological field theories. But are there some other directions that you think are still required to, that still deserve some attention,
Oh
in
yeah,
this
they're
particular
huge.
program?
Yeah. Yes, they're huge ones. First of all, Lurie's paper did not prove the cobordism hypothesis
Yeah.
that James Dolan and I came up with. Lurie did
Hmm.
amazingly good work. He took our so what is this cobordism hypothesis? Basically, you could say it's a classification of topological quantum field theories. A topological quantum field theory is a kind of quantum field theory where you don't use the space-time metric at all in describing the Lagrangian of the quantum field theory. So it's automatically diffeomorphism invariant. Let's simplify it that way. And it turns out that that we came up with a beautiful and categorical classification of the topology of manifolds, which you could use to get a classification, at least abstract kind of classification of topological quantum field theories. We just guessed this thing as a kind of hypothesis. So it got called the cobordism hypothesis. Lurie reformulated it. He stated it a different, better way that allowed him to sketch a proof, a 54-page long proof of the hypothesis using concepts from N categories that had not rigorously been defined at the time. So it was a sketch of a proof that required further development of the theory of N categories to become an actual proof. People have been working on filling in the details of that. So people have not completed that proof. People have found other ways to try to carry out the proof. I think there's still a lot of interesting work to be done just to clarify that whole situation. Part of why we got so excited about formulating it is because it used a whole bunch of concepts from N category theory that seemed to make sense and seemed to work in examples, but we just had no idea of the best way to formalize them, much less prove them. And so it was like a spur to further development. Now once you have this abstract classification of topological quantum field theories, it's still very far from a concrete classification. So if I asked you, like, what are all the topological quantum field theories in 4 dimensions, this theorem would not be very useful. It would be useful, but it would not give you an answer. It wouldn't give you an answer in the form of like a list of them. It gives you a very abstract description of them. So you still have a lot of work to do to find them and classify them. And so it's definitely a huge step in the right direction. And I'd say, like, in dimensions 0, 1, and 2, they're very well worked out. In dimension 3, they're fairly well worked out by now, but still, I'd say with some tricky questions. Dimension 4, I think it's still pretty darn open to try to understand what are the 4-dimensional topological quantum field theories. Dimension 4, in terms of topology, well, in terms of physics, of course, it's exciting because for some reason or other, we're living in 4-dimensional spacetime. In terms of topology, it's interesting because 4-dimensional topology is completely different than lower dimensional topology in several ways. One way it's different is that in lower dimensions, there's only one way to make Rn, n-dimensional space, into a smooth manifold, which is the obvious way. So a smooth manifold is a space that's covered with coordinate charts that look like ordinary n-dimensional Rn. I hope I can say Rn in this podcast. It means n-dimensional Euclidean space. Yeah, I've seen some of your podcasts and I think, okay, good. I can talk at this podcast because I can say something like Rn and they won't say like what. So you can cover like the sphere with a bunch of copies of the plane, like an atlas of maps. Now for R4, it's proof that there are weird ways to cover R4 with copies of R4 that make R4 into a smooth manifold that's not the usual R4, which is very bizarre. And it was proved with the help of a lot of physicists like Witten and others, Seiberg and others, and a lot of mathematicians, and they showed that using gauge field theory in 4 dimensions, they could prove the existence of exotic 4-dimensional spaces, exotic R4s. And there are uncountably many ways to make R4 into a manifold. This is bizarre. It's especially bizarre because you should be able to describe these things, these exotic R4s, fairly concretely. but it's hard to get your hands on them and describe them. The original proofs that they existed were to some extent proofs by contradiction. It doesn't actually hand them to you. And so better understanding of four-dimensional topological quantum field theories in terms of combinatorial or algebraic data, stuff that's like you can describe using a finite amount of information, would be really helpful, I think, in really more deeply understanding these exotic R4s. And I think probably there's some connection between these exotic R4s and other exotic phenomena in four-dimensional topology and physics. There's a lot of thoughts about that, but they haven't really solidified into anything very convincing yet. But so that's like one direction to go in. But I should say that like a more practical direction is that there's now getting to be a lot of interest in topological quantum field theory in condensed matter physics. So the quantum Hall effect is an effect that is connected to a certain three-dimensional quantum field theory. Chern-Simons theory again. But people discover that like deeply understanding the quantum Hall effect, which is an effect that occurs in thin films of material, superconducting thin films, really uses higher category theory. There are really cool papers connecting quantum condensed matter physics to higher category theory, by which I mean, in this case, like 1, 2, and 3 categories. So that's connected to this cobordism hypothesis, but it's sort of more at the lower dimensional level where we can get our hands on things, but there's like connections to actual experimental physics there.
So I'm pretty sure that you are familiar with the work that has been going on for the last 10 years, especially on something called generalized symmetries, where they found out that global symmetries can be written in terms of topological operators, right? And there, people have come up with the idea of something called non-invertible symmetry, where you may have a transformation that doesn't have an inverse. And there people do use, categories, because there are some, symmetries that are not described by groups, but they are described by categories. For example, there is this very famous conformal field theory called Ising CFT, and it has this, symmetry called the Tambama, a TTY category. So what do you think about this program? Do you think that this is, an extension or an extension of, or in the same spirit of the program of categorification that you were looking for when you wrote that paper, or do you think that this is a bit different?
I'm sorry to say that I know almost nothing about this. I've heard people talk about it. I've
Mhm.
never studied it at all. For the last 10 years, I've been working on completely different things. And I find that it's just better for me to think about what I'm actually working on.
Mhm.
So I would love to learn about that stuff. And I think I may be forced to learn about that stuff because, see, I was retired, but then I decided I wanted to get out of the United States for some mysterious reason. You maybe can perhaps guess what it is. And so I got this job at the University of Edinburgh, and I got hired by this group. I got hired by both the mathematics and physics department, and I got hired by this interdisciplinary group called Algebra, Geometry, and Quantum Fields. And there are people in this group who are working on topological quantum field theory and who understand these things like these non-invertible symmetries. So all of a sudden, I'm going to be very embarrassed. I'm not actually all that embarrassed, or I wouldn't be talking about it, but I'm going to be very embarrassed because I'm going to meet these people and they're going to think I know what they're doing because I used to be interested in stuff. And so what I'm going to have to tell them is I'm going to say, sorry, I don't understand this stuff at all. Could you explain this stuff to me? Or else maybe they'll just like point me to a blog article.
Sure.
uh, and so I will learn about it. And I think it's bound to be fascinating. So it's got to be related to this other stuff I'm talking about. I just can't
Hmm.
imagine that it's unrelated. But unfortunately, I have nothing to say about how it's related right now.
Oh, it's okay.
Maybe
I mean,
maybe you can ask me in 3 years, and then I'll tell you.
sure, sure, no problem.
Yeah.
I'm pretty sure that it will not be hard for you to learn that, because when students learn it, the biggest obstacle that they face is to learn category theory, and that's something
Uh-huh.
that you already know, right? So you should be
But if
fine.
that's the biggest obstacle, then it sounds extremely easy. But I suspect there are also other obstacles. Um, One problem, is that like the more math and physics the more questions you have is when you start trying to learn something. And so sometimes when you don't know too much, it seems very easy to learn something because you just like read the stuff that's on the page and you learn it and then you know it. But if you like have studied all sorts of stuff, it becomes hard to just like read the stuff on the page and go, yeah, yeah, yeah. You go like, what? What the hell is that? That reminds me of this and this and this and this.
Yeah.
And so yeah. So I'm sure that as I try to learn this stuff, I'm going to be like wondering about all sorts of things. Now, in the long run, that can be very helpful, right? Because then you like the goal is ultimately to get a deeper understanding of what's going on.
Hmm.
But in the short term, it may be frustrating. So anyway, I'm looking forward to it.
Sure. Okay, so there are some other topics that people who are interested in category theory work on, and one of those topics is called topos theory. So can you tell us what is topos theory?
Sure. Well, I don't think I can tell you what it is, but I can tell you, I mean, I can, but you don't want to hear about it. But I mean, I could tell you what it is. Okay, a category theory, a topos is a category with finite limits, finite colimits, a sub-object classifier, and it's Cartesian closed. There, now you know what a topos is. Um, but I don't think that's probably very helpful unless you
Hmm.
already know what a topos is. So a better way to think about it is that Grothendieck was trying to solve some very fascinating number theory problems. And he revolutionized algebraic geometry in the process of trying to solve these problems. They're called the Baez conjectures or Baez hypotheses. And he realized that you should think of a solution to a bunch of polynomial equations as a kind of space. And that's easy to believe if you're like dealing with complex solutions, like a parabola, a hyperbola is a kind of bunch of solutions of equations. But he was studying solutions that might be like solutions where you only care about the integer solutions, or maybe solutions where you only care about the solutions in integers mod 3. And those don't look much like a respectable sort of space, but he said it's got to be like a space. And so he was led through a long chain of research to grandly generalize the concept of space to this concept of a topos. And it turns out that for each kind of topos or generalized space, you get a new kind of version of set theory. It's really amazing stuff. So if your space is just a point, the most boring space of all, then the kind of set theory you get is just plain old set theory, just ordinary sets. But if your space is more interesting, you get a more interesting kind of topos, where instead of just having the concepts of true and false, the way you have in ordinary set theory, in ordinary set theory thing, like an element is either in a set or not, a proposition is either true or false, and so on. But in more interesting topos, you can talk about a proposition being true in some region of space. You say it's true in here. It might not be true out there, but it's true in here. And so for each region of space, you get a different concept of truth in that region. So you could call it local truth. Um, I mean, it even applies to ordinary life. So for example, like you could ask the question like, is it over 70 degrees Fahrenheit? Sorry, I'm using Fahrenheit. And the answer, someone wouldn't say like, well, what the hell do you mean by that? Where? Where? But you could say, oh, and what I meant was like in this room, is it 70 degrees Fahrenheit? And then they could say, yes, it's over 70 degrees in that room, right? So a question only makes sense in a region. It makes sense. It has a truth value in a region. So Topos theory is a generalization of set theory that deals with local truth. Uh, and and it's remarkable because first it was developed for the purposes of algebra and number theory, very highbrow number theory, developed by Grothendieck, which at the time nobody wanted to follow him in that direction. Even the people who were working with him at the time, they said like, yeah, that's a little too far out. I don't want to think about that. Um, and it's only come into vogue more recently in work on things like number theory that people have actually started using Topos theory. Um, it took like, like whatever, I don't know, decades for people to catch up with what Grothendieck was doing. But in the meantime, a bunch of category theorists, especially this guy Levier and his partner Tierney, were the ones to realize the deep connections between Topos theory and generalized concepts of logic. And so they pushed Topos theory in a more logic-flavored direction that has developed the implications it had for thinking about logic. And that got caught on by category theorists, caught on to that very much. So category theorists, some of them like Topos theory a lot. And so they'll say, like, if you tell them some fact, like, what's a fact? I can't think of a fact right now in mathematics. Like a fact, like, yeah, like, is every function from the real numbers to the real numbers continuous? That's not a fact, that's a question. So if you're dealing with ordinary set theory, you'll say, no, of course not. There's lots of functions that aren't continuous. But they'll say, well, yeah, that's true in your topos. That's true in the ordinary topos of sets, that it's not every function is continuous. But there's another topos where it is true. And so they're like other toposes where you can develop the theory of the real numbers in that topos. And there it could be, in some of them, that every function from the real numbers to the real numbers is continuous. And they're very interesting toposes with other properties. So they're like alternate universes in which you can do mathematics. And well, there's a lot to say about that, but that's some of what Topos theory is about.
I see. So another topic that you have worked on, recently is the topic of network theory. And when you naively look at, what network theory is, it looks a lot like, graph theory. So can you tell us what network theory is, and is it just graph theory in a different packaging, or is it different?
It definitely uses a lot of graph theory. So it comes from the realization that a lot of practical people, a lot of scientists, like biologists, chemists, and also engineers, like electrical engineers, they will draw what they're studying using graphs. So you've seen pictures of electrical circuits, I hope. I've heard that like now electrical engineering departments are so excited about computers that they don't even teach, some of them don't even teach students about resistors and capacitors anymore, which I guess means that like you're hoping that like people in China are actually going to make the electrical circuits. But anyway, once upon a time, electrical engineers knew about electrical circuits. I think they still should. And they draw them as graphs, a bunch of wires connecting, meeting at nodes and having little resistors. But they're not just plain graphs. They're graphs where the edges have information on them, like what's the resistance of this resistor, or something like that. And they study them and work with them that way. And they show that like any such circuit, let's think of like an analog circuit, gives rise to a set of differential equations, describes how the current and voltages change over time. And so the whole process of designing an analog circuit is figuring out like what kind of circuit do you need to give rise to differential equations that will give rise to solutions that obey some behavior that's what you want. It will do what you want. Like be an amplifier or a high frequency filter or something like that. And meanwhile, chemists are drawing networks of a completely different kind called chemical reaction networks, where the vertices or nodes are different collections of chemicals, and then the edges are different chemical reactions that go from some bunch of chemicals to another bunch of chemicals. And all these different subjects are working with graphs, but they're not just studying graph theory, they're studying graphs that have extra information on them, and they're using that information to do interesting forms of reasoning. So there's like a whole subject of mathematical chemical reaction network theory that shows like which kind of chemical reaction networks can give rise to a single stable equilibrium state, or which kind of chemical reaction networks can give rise to pulsing chemical reactions where things keep wiggling back and forth and so on. And so I realized that it's really sad that these different subjects aren't talking to each other enough. They don't go about it the way a pure mathematician would do and say like, okay, there are like dozens of different kinds of networks that people are studying. There should be a general concept of network that covers these different concepts. There should be general theorems about it, which will, of course, not cover all the theorems, but will help cover some of the theorems, and then they should be studied, individually, case by case as part of the larger theory. And so network theory is trying to sort of unify those different practical disciplines in various ways. I should say it's just getting started. So far, a lot of the work on network theory has covered only the most simple-minded concepts that are so simple that nobody ever bothered to formalize them before. For example, in every kind of network, you have the ability to take networks of that kind and stick them together to form bigger networks. And you want to analyze networks that way. So like if you're building a big complicated electrical circuit, you might design different parts and then imagine sticking them together. So now category theory is perfect for that, because what you're saying is that these different parts, they are morphisms or arrows in a category, and you're composing them, sticking them together. So all the business of how you can stick together systems to form larger systems is where category theory excels. In some sense, that's the very trivial aspect of the whole subject, because electrical engineers just take it for granted that you can stick together electrical circuits to form better, bigger electrical circuits. But it turns out that nowadays people are starting to write software that's trying to be able to let you easily manipulate networks of general kinds. There's already software for drawing electrical circuit diagrams, and there's already software for drawing chemical reaction networks, and there's already software for blah, 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 blah. But we would like to have general purpose software that can let you deal with all these different kinds of networks and let you do things like translate one kind of network into another, or build systems that combine networks of different kinds and so on. And when you want to try to do those more sophisticated tasks, you need a general theory of networks so that you know like what's a network and what are the different kinds of networks. So people at the Topos Institute are working on such software now. And to develop that software, it really helps to use a lot of category theory, because you want to work at a pretty high level of abstraction so that you can then specialize down to lots of special cases without having to redo everything every single time you cover a new case. So I'm working on that kind of stuff, yeah.
So you have kind of, mentioned something that was, related to the next question that I wanted to ask you. So you did this work with Fong and Pollard regarding networks that, represent open systems, and these networks have inputs and outputs. And as you said, that you can stick together networks, which is something referred to as compositionality, right? So
Mhm.
when you were doing that work, what were the motivations to, introduce these kind of networks? Now you have mentioned one of them, which is circuits, but did you have some other motivations? Because you also wrote this paper with Lynch and Moeller regarding, compositional thermostatics. So was that another motivation to, introduce these kind of networks?
I mean, my real motivation was for all of these projects was I was trying to understand the general concepts of network theory and try to see how those concepts are hiding in many different subjects in science and engineering. So see, what's so interesting to me is that when you read a book on electrical engineering, some of these books are very mathematical. So they'll even like include theorems and of about like complex analysis and poles and the complex plane and stuff like that. But then they will also draw lots of pictures of electrical circuit diagrams and work with them. But they never mathematically define what an electrical circuit diagram is. They don't think that that stuff is mathematics. They think that stuff, those pictures of these electrical circuits, is just like the stuff that we draw to help us understand the mathematics. And that's very strange from a mathematical point of view. Um, to be like doing this very mathematical subject and manipulating these diagrams, but never like thinking of them as part of the mathematics. And see, that happens in lots of subjects. For the chemical reaction network theory, maybe they're actually starting to formally define what a chemical reaction network is, but there are a lot of basic things that they do with them, which they have not bothered to formalize. And so what I was trying to do is to find the general concepts of network theory that people in all these different subjects are using and formalize them. That is to like give them mathematical definitions. Um, and the only way I could see that to go about doing that was to consider lots of special cases. So I had to like learn electrical uh, engineering. I mean, a tiny amount of electrical engineering. Electrical circuit theory is probably a better name to say what I was learning. Learn chemical reaction network theory. With Fong and Pollard, we were studying Markov processes, so I learned about that. And so on and so on. With later on with Owen Lynch, he had the idea of like when you're studying thermodynamics, you'll often see these systems that look like you have like a piston and you like stick one piston next to another piston and you talk about like the Carnot cycle and so on. Uh, and so he realized that that could fit into this framework as well. And so what happened was at first I just started trying to go through subject after subject. Very luckily for me, my very first student working on this was Brendan Fong, who was incredibly smart. And so I wanted him to just work out the theory of electrical circuits in a mathematically rigorous way. But he did much more. He developed a general framework called the theory of decorated cospans in his thesis, which was a general theory of networks. Um, and so then I thought, well, okay, great, that's great. So then I would try to use that theory to study these other subjects and to see if they fit into this framework or not. Because if they didn't, that would mean that I needed new concepts. With my student Kenny Cursor, I realized that there's a simpler approach, which we call structured cospans, that handles a lot of cases, but it turns out not all the cases. So so what I was doing in these different papers was I wasn't really trying to make progress in these different subjects. I wasn't really trying to say like, hey, electrical engineers, like here's some new thing that we can do that you're going to love. Um, Instead, what I was doing was it was like the flow of information was the other way. It was like, hey, there's all this stuff these electrical engineers are doing. They don't think it's mathematics. They just think they're like drawing pictures of stuff and sticking the pictures together. But hey, mathematicians, this is actually category theory of a very interesting sort. And similarly with the other subjects. So it's bringing in information into pure mathematics from applied mathematics. That's the first step. Now, I would be happy to just keep doing that my whole life because it's so much fun. But then what happened was some people started saying like, hey, once you've formalized these concepts, we can develop computer software that deals with these formalized concepts and start creating new software that deals with general networks. And I should give a lot of credit to James Fairbanks and Evan Patterson for starting to create a framework, which they called algebraic Julia, which is like a computer language that lets you develop, that lets you program using category theory ideas, and to instantly start turning that framework towards working with things like chemical reaction networks and so on. And that wound up being used for our work now on models in epidemiology, because epidemiologists also draw lots of diagrams of networks of like how a patient could become sick and then go to the hospital and then turn into something else and go over here and over here. They draw these very elaborate, complicated networks. My collaborator, Nate Osgood, was heading one of the heads for COVID modeling in Canada, and they were drawing these networks for COVID modeling. They're so complicated, you can barely even see them on a page. They're like super complicated. And so he realized that category theory could make this modeling better. And so we're working on that now. So it all became rather practical. But my initial goal was just like to understand what applied mathematicians and engineers were doing using category theory to understand what they were doing.
So just as an example, for epidemiology, what would be the, networks that you compose with each other? So like population of different cities, is that the,
Yeah, that could easily be one. Or for example, you could have different hospitals. You could have, but there are also other things that, for example, you might have, for example, let me think of a good example. There's a lot of interest now in, for example, in how a lot of people have diabetes these days in the United States and other developed nations because we're eating like too much corn syrup, basically. So type 2 diabetes is affecting huge fraction of the population. And so now there's problems like what happens when someone's pregnant and also has type 2 diabetes. So what people are doing to try to understand this is you take a model of pregnancy and a model of like the fetus and how the fetus interacts with the pregnant woman, and you want to combine it with a model of type 2 diabetes. So there you have like two models. You might draw each of them using some network, and then you're trying to stick them together because you're trying to create a combined model of two different situations. And so that's the type of thing that's an example that's sort of a little less obvious than the ones that we started out talking about, where you're combining models. And in fact, that model is the one that we're going to try to work on in a project in Edinburgh this summer. We're going to try to develop a model like that. There are known models like that, but we're done by my friend Nathaniel Osgood, but we're going to try to, and other people, and we're going to try to do those models in our new mathematical or software framework to prove that it's like easier to combine models now than it was before.
I see. So you're quite well known, in the physics community because of your, writings on the internet from since the late 90s or early 90s, actually. So you used to have this, the thing called, this week's,
This week's
finds in
finds in
mathematics.
mathematical
Yeah,
physics.
in
Yeah.
mathematical
Yeah.
physics. So how did that project start? Because I think that started in early 90s when internet was, quite new. So how did
Yes.
you come up with this idea, in the early 90s?
Yeah. So that was really interesting. So it happened because I got a job at the University of California in Riverside. My girlfriend, who later became my wife, had a job in New York. So I was far away from her. So I was very lonely in the evenings for many nights. And so I had to figure out things to do to keep from going crazy. Um, and the internet existed at that time. The World Wide Web did not yet exist. People communicated but using something called Usenet. So you could put software on each server that would send and receive messages similar to email uh, to other servers. But unlike email, these messages were all publicly available to everyone on the network. So there was a kind of piece of software you could have that you turn it on, and then you just see all these news groups. They're called different things, different discussions groups about different subjects. So I mean, you can think of it as like a primitive version of what you see on Reddit now or something like that. Um, but before the World Wide Web. So you're just dealing with like a command line interface kind of situation. And so there's one called sci.physics where people discuss physics, and there's one called sci.math where people discuss math. And so I jumped in there and I started talking to people, and it was tons of fun because this was like the first time that people were like beginning to communicate with each other on the internet worldwide from different universities. It was mainly universities who had internet access at that time at first. Um, and so I started explaining and arguing about physics and explaining physics. And then eventually it grew to the point where I said, like, hey, it'd be really fun if every week I would just like write a little article about the papers I've been looking at this week, the physics and math papers I've been looking at. So that was the idea of it. And I wound up not doing it every week because it's hard to keep doing something every week. But I kept doing it for a long time. And I still kept calling it This Week's Finds in Mathematical Physics. And it kept growing and getting more serious as it went along. And right now, well, I quit after the 300th issue. I am now slowly turning all those entries into basically sort of books, just so that I can put them on the archive and just sort of give them more chance of surviving in the future. And I discovered that like the first 50 weeks were like, I don't know what, like I can't remember, like 150 pages long. Then like the next 100 weeks was like 250 pages long, and they kept getting longer and longer. So I realized that what happened is I like kept making them bigger and bigger, and I eventually probably got sort of burnt out, and I had to quit. But the total is a couple thousand pages of stuff, and it just explains a whole lot of math and physics, and a lot of people seem to still find them useful. They're more useful when you click on the papers that I'm talking about and you actually read the papers, of course.
Right. So as you just mentioned that when you started using the internet and you started to explain physics, I can imagine that since it was the internet, the people who were reading the stuff that you were writing are not all physicists themselves. Some anyone can join the internet, right? So there you may have come across some what we call crackpots. So is that the reason why you developed that crackpot index that's very well known, or were there some other reason?
Yes, that's exactly why. So the interesting thing is at first, the internet was heavily a thing of academia. I mean, if you go back even earlier, you discover it was called ARPANET, and it was a Defense Department experimental method of communicating information. And then it sort of grew to certain universities that were connected to the military. Then it spread to universities. And so when I started, it was mainly people connected to universities. And so it was very fun talking about physics to grads. It would be like, I don't think undergrads typically had an internet account back then. So it'd be like grad students and professors. But unfortunately, the internet caught on in popularity. And so more and more people got involved. And so what happened was people started learning about these physics and math discussion groups. And some of them were non-experts who were really great people, really interesting people who, normal, normal people who would like have lots of questions and things like that. And that's fun. That's part of how I got into explaining so much math and physics. I got really a lot of practice explaining all sorts of stuff. But there are a lot of people out there, not as many as ordinary people, but there are a lot of people who come up with their own theories of physics and sometimes their own supposed proofs of solving famous math problems. And when they discovered that there was a way for them to communicate with experts around the whole world, they got really excited and they started telling us their crazy theories. And so these crackpots, I'm not too shy about calling them crackpots. These crackpots, previously, they would just like send letters to academics. Or maybe sometimes they'd like show up in the university department and actually like knock on the door of a professor. But now all of a sudden they were able to communicate to large groups of people at once. And I discovered, well, so we had to form what are called moderated news groups, where you had a moderator that kept out the crackpots. And so I was a moderator on the group physics.research. And so I learned that the crackpots have identifiable characteristics. There's certain specific things that they tend to do and I made a list of those things. That was my somewhat joking article, the crackpot index, which you can get online if you just type crackpot index into Google. But all those entries, while they're sort of funny, they're all true. They're all exactly things that crackpots actually do. Now, I'll add that in the last couple of months, there's been a huge new trend in crackpots, which will force me to update the crackpot index, which I haven't done for a long time. And the new trend is that they're starting to use ChatGPT and other large language models to help develop their theory. Because if you're a crackpot and you start trying to discuss your theory, no one wants to hear about it, essentially. I mean, there might be some people who would, but almost nobody does. But if you're talking to a chat bot, they will be very polite and they will discuss your theory and they may correct it a little bit, but they will, it turns out that if you like keep talking to one of these chat bots about your theory, they will sort of tend to wind up agreeing with your theory. They sort of they're designed to be cooperative, and they will tell you useful things to help you develop your crazy theory. So now crackpots interact with these chatbots and develop these elaborate theories that are helped by the chatbot, and they don't make any more sense than they used to. They're not any improved at all. It's just made them go more crazy, because basically it's as if you're like a crazy person and then you like finally find somebody who's willing to act like they believe everything you say, and then it just sends you down the rabbit hole of confusion even worse. And so now every day I get at least one email from a crackpot, and most of the time often they will admit that they've developed their theories with the help of these chatbots. And of course, all this nonsense that's going on, it's like a tiny fraction of the amount of nonsense that's related to things like people who don't believe in vaccines, people with political conspiracy theories. I think of like certain crazy political beliefs as being just as crazy as these other things. So I think the internet has led to like an explosion of crazed behavior. And so now the physics crackpots are just like a tiny fraction of that. And they're, in some sense, the least harmful of the one of the least harmful forms of all this craziness. I think the most important thing is that there are far worse crackpots in issues related to health and politics and all sorts of other things. And so, in some sense, being a physics crackpot is one of the best kinds of crackpot to be because you don't wind up hurting anyone much except yourself by having some crazy theory.
I mean, but for example, if there are people who say that, 5G gives you COVID, do you consider them to be physics crackpots or not?
Uh, well, no, that's not what I meant. Yeah, no, that's what I meant by like a health crackpot.
Okay,
The
I
kind
see.
of crackpots that write to me never talk about that. The kind of crackpots who write to me say always have like a new theory of quantum gravity. I got a I got a theory. Some of them involve the Octonions, all the things that are supposed to be interesting to me.
Hmm. Yeah, that makes
Which
sense.
I look at them. I look at them. There are people who write to me who have done interesting things who are amateur mathematicians and physicists. So it's not true that you have to be a professional academic to do useful or interesting work. But there is so please don't I don't want anyone to think that when I get an email from someone who's not a professor, I instantly assume they're a crackpot. I look at what they say, and you can tell fairly quickly if you've mastered the crackpot index, you can fairly quickly tell who's telling you something interesting and who's telling you something that probably won't be interesting.
So initially, when wrote the first draft of the crackpot index, it had
Mhm.
like 17 points, and then you added like 20 more, and now it has 37 points. Now you're saying
Okay.
that you
You
will add.
you understand, you remember this better than I do. Okay, that's good.
Well, probably because I read it some days ago. That's why. So,
Uh-huh.
so now you're saying that you will add more points. So, do you know how many points are you gonna add?
You mean top issues? Yeah. I need, so there's got to be something that says, well, I mean, this won't be what it is, but I got a great line in my email recently. Someone said they've been working on this theory of quantum gravity, which they've developed rigorously with the help of large language models. So like anyone who says that, I instantly know, oh no. So so there's got to be something that's sort of like that.
Okay.
They basically announced that they've been working with chatbots or large language models to develop their theory of physics. I don't know if I need to do more than that one, if I phrase that one correctly.
So, since we are talking about AI, let's go into an adjacent direction that is kind of related to it. So
Mhm.
recently you gave this talk regarding the future of physics, and one of the topics that was discussed was again future of physics in the context of AI. So what do you see the way people do physics can change in this age of AI. I mean, we can use it for good things, of course, as well.
Right. I didn't say anything about that. I I I believe that right now the most powerful effect of AI is a negative effect of large companies shoving AI down our throats and businesses trying to figure out ways to replace people with AIs, even though it may make the quality of various services worse. I mean, if it makes it better, okay. But basically, I think corporations would be happy if they didn't have any people in the corporation, if they could still somehow do the same approximately the same thing. So I'm much more concerned about that aspect of AI than any of its positive effects, because it's a bigger deal right now. But certainly, yes, I mean, it's certainly possible for AI to have positive effects, and it would be great if after some kind of massive, I think we need a lot of legislation and a whole new reformulation of society to deal with AI. But after that, maybe then the positive effects can start to become more significant. It's an interesting question how much. I mean, let's imagine that we had AI that we could actually trust when you ask it questions about physics, like questions to known physics problems, for example. Right now, I don't trust any AI that I use. I sometimes ask it questions, and then I use it to find references to papers, because I don't trust what the AI says, and I want to see what some people actually said, which is already helpful. But suppose you got into a situation where you could actually most of the time trust the AI. So for both math and physics, it raises a really interesting question of like, why are you doing math and physics in the first place? Because for me, like when I'm doing math, I usually want to understand in quite a lot of detail every aspect of what I'm doing. So for me, there are times when I'm lazy and I use theorems whose proofs I don't understand. But I think it's a very small fraction of the time, actually. Because for me, the fun of mathematics is to actually understand everything. So I would like to be able to like be on a desert island with a bunch of paper and a pen and be able to do mathematics. I mean, if I'm not saying that's my preferred way of doing it, okay, but I'm saying that I would like to get, I feel like when I understand something, I can do that. Very usually it happens when I'm on a long plane ride. I have nothing to do. I just work on mathematics. So, but you can imagine if that's your goal, then to some extent AI is not all that much more helpful than like talking to people. I mean, it's good to talk to people. You learn a lot of stuff. But ultimately, you hopefully have within yourself the full knowledge of what you're doing.
Yeah.
But you can imagine people taking a very different attitude. You can imagine saying like, I don't really care about the proofs of all these theorems that I want to use. I just want to use these theorems to prove other theorems. And I just want to like know whether something's true or not. I don't care so much about all the details of why it's true. So then you could try to, there are already some people, I suppose, who do mathematics that way, and they like cite this theorem and cite that theorem in their paper, and they try to build a paper by gluing theorems together. It's a very dangerous thing to do because mathematicians don't always state the theorems quite precisely in a way that lets you glue them together if you don't understand what the theorems are saying. But you can imagine people taking that approach. And so then you'd get some new kind of mathematics that would be more like other subjects and less like what I think of as mathematics. More like other subjects because you like rely on a lot of things working. So, these days when people do serious software design, they are often like using all sorts of software packages and sticking them together and composing them in different ways where they don't necessarily understand how the details and all the different packages work. They just sort of believe that they do function correctly.
Right.
So that may be how mathematics and or theoretical physics, maybe that will happen. Maybe those people will be able to make progress faster than people who try to understand everything themselves. We'll see.
Right. I mean, so there is this inaugural situation that happened, if I'm not wrong, in the 70s, when people used computers to prove the four-color theorem. And, when that theorem was proved using computers, Michael Atiyah said in a BBC documentary, almost the same thing that you just said, that we are in the business of mathematics to understand. We don't want just answers, we want to understand. So do you think
Yes.
that we are in a similar kind of situation with AI now that people were facing in the 70s with computers?
Well, the funny thing about AI is that it's similar in some ways, but well, the AI, there are different kinds of AI, but the large language models, the big difference is you can't trust that they're actually telling the truth, right? So the people who proved the four-color theorem using a computer, they knew for sure that it was true. So that's a big difference than like asking a large language model a math question. It's fun to do that, by the way. Um, yeah, I really recommend it, doing it for a while. Like start out with some easy question. If it's like a question where the answer is known, it's very often they will give you the correct answer. And then if you start making the question harder, you reach a point at which they just start making stuff up. It's just baloney. Um, so for me, most of the questions I'm really interested in are the ones where nobody knows the answer. And so then these large language models aren't helping me so much. Wow, I'm already forgetting your actual original question, which is a little bit different. Oh yeah, so there are other people who are using computers and AI to do rigorous proofs of things.
Mhm.
So you can definitely use AI and you can use proof search methods, which are a different kind of AI to like automatically search for proofs. But when it's finally found one, it's like know for sure it's a rigorous proof. And it could be a proof that's so long that you don't personally understand it. People are doing that so far mainly for theorems that involve checking hundreds or thousands of cases. So you like do some of the work yourself that you understand, and you reduce a sort of infinite problem down to like 1,000 cases or something like that. You don't know how many cases maybe, and then you let the computer do the rest of the work. So for example, uh, there are some important problems in packing things. For example, like what's the densest way to pack spheres in three-dimensional space? Well, Thomas Hales first came out with a computer-aided proof where he sort of understood the steps, but then there were lots of calculations involving millions of, I don't know how many, lots of cases that he left to the computer. And he's going on and doing other proofs like that. So, yeah, so the question is, I'm getting back to your question. So your question is like, is that some Are we, is that, what kind of mathematics is that? What's the use of understanding that something like this is true without understanding much about why it's true? If it was a practical problem, if it was a question where you needed to know the answer, like to build an airplane or something, then it's easy to say, yeah, well, good, it's very important to know that it's true. I don't care why it's true, but it's really crucial that it is true, right? If the plane will crash if it's false. In some sense, that's what you're doing when you're like simulating an airplane wing using some complex simulation. You're solving a bunch of PDE. You don't want to go through the calculation by hand because it would take millions of years, but you want to be damn sure that the simulation is correct. But for theoretical mathematics, like the densest packing of spheres, it's not it's not a practical problem. So the question is, how much fun do you have really in understanding it versus how much fun do you have in in writing a complicated computer code that will prove it without you understanding it. I think the people who do this kind of work, they must enjoy I mean, for that kind of thing, you have to do a lot of hard work with the computer programming. You don't just ask the AI, is the four-color theorem true? You have to like, Hales had to do huge amounts of very tedious computer programming to get the computer program to actually work. So he had to enjoy the process. Um, so that's a different kind of enjoyment, is all I can say. So like, for me, it like makes me a little happy to know that, yes, now we know that the obvious densest way to pack spheres really is the densest way, we know for sure. But then I would instantly say, like, okay, but it would be really nice to have a proof that you could understand. That's when it would become fun for me. Like if somebody said, like, well, we can find an elegant proof that uses some branch of mathematics that we didn't know before, or that we didn't know it was useful for this before. For most mathematicians that I talk to, the fun would start when we got to actually understand the proof. Um, so
Well, yeah, you're right that on the face of it, it doesn't look like a practical problem. But there was this interesting thing that I learned, and I was like, okay, even this problem can be practical. I mean, not today, but it was like practical in the first half of the 20th century. So there's this book by Mark Ronan. I think it's called Symmetry and the Monster. I think this is the name of the group one book, where he talks about the story of the classification of finite simple groups.
right.
And one chapter of that book is about Leech lattice, which exists in 24 dimensions, right? And in that chapter, he talks about this story where Claude Shannon, who was the one of the pioneers of information theory, he was working on a problem of this thing, right? A problem of sphere packing, right? And the problem was practical because it turned out that if you can find out the densest packing of the sphere, you can actually
Mhm.
reduce the distortion in radio broadcasts. So,
Yeah, that's true. There's this great book called Sphere Packings, Lattices, and Groups, or maybe, but
mhm.
it's by Conway and and someone else whose name I should know, Sloan. Um, And yeah, so you can use sphere packings to design codes. There's this 8-dimensional sphere packing, which has very recently been proved optimal by this Ukrainian woman and some collaborators, which is it turns out to be related to E8. It's called the E8 root lattice. And that E8 lattice was used, well, something connected to the E8 lattice, not the E8 lattice itself, but something very closely connected, was used for codes to transfer information from the first unmanned Mars missions. It's because they wanted a very efficient coding of information because that spacecraft could only send tiny amounts of information back to Earth. So yes,
Right.
it's true. The things that don't look practical can turn out to be practical. Yeah, so I agree with that.
Right. Okay. So I have one more question, and then I have some people's questions, and then we can wrap it up. So one question
Uh-huh.
is that, in the talk that I was mentioning, you mentioned some problems like, polaritons. I mean, which are objects in condensed matter physics and artificial special relativity, semi-metals, topological matter. So these kind of problems do require attention, and that brings this question to my mind. That do you think that there are some topics in physics that have not got as much attention as they deserved?
Uh, I'm sure there are millions of them. Most of them we don't even know what they are yet.
Mhm.
Um, so so let's see. You're supposed to name one. I'm supposed to name one that you. So yeah, I mean, I think well, there are some hugely important ones that have gotten a fair amount of attention, but I think still not nearly enough attention. So here's one. Nobody knows if the standard model is mathematically consistent.
Yeah.
That's ridiculous, right? So I mean, that's like an important physical theory. Um, no one has formulated it in a mathematically precise way. And there are even bits of evidence that it might not be mathematically consistent. If you look at some of the recent literature, you'll see that the Higgs mass and the top quark mass are in a range very close to the range where some heuristic calculations suspect that it would destabilize the vacuum. That is, that the apparent that ground state is not the actual ground state. I mean, yeah, the Higgs mechanism involves like a field rolling down to the bottom of some trough, and then when it's at the bottom, that's where we are now. But it turns out that if the basic constants in the standard model are in certain ranges, that's actually not the bottom. It could go further down. I could give you references to this. So what does that mean? Well, if the supposed if there was like no ground state, if the energy could go down indefinitely, which is what the danger is here, it basically winds up meaning that the model is not consistent. The standard model is not consistent. I mean, probably. But so that's the fact that this is like something that nobody knows for sure is pretty remarkable. And when you start studying these type of questions, you see that there's very little that we understand about, for sure, about interacting quantum fields in 4 dimensions. The mathematics is just is too hard for us today. And so that's why Ed Witten helped formulate one of the Millennium Prize problems. There are various $1 million prize problems. And the funny thing about them is that almost all of those problems, the question is completely precisely stated, like the Riemann hypothesis. You can say exactly what it is. But one of those problems, the problem is not quite precisely stated, which is strange. And that problem is called the mass gap problem for SU2 Yang-Mills theory. And you're supposed to prove that in 4 dimensions, that the quantum field theory for SU2 Yang-Mills theory, not coupled to any fermions, so-called pure Yang-Mills theory, is consistent, and that there's a gap between the vacuum energy and the lowest possible next energy, because you would have glue balls. You'd have a particle called a glue ball on this theory, and it would be stable and would have some lowest possible energy. So the funny thing is that no one has actually rigorously defined exactly what it means for Yang-Mills theory to exist, so that there's some wiggle room in stating, in proving that it exists and that it has this extra property. But the fact that that's $1 million problem that hasn't been solved shows that the standard model, which is like a more complex gauge theory, is further in the away from being fully understood. And I think this is really interesting. I think this is really interesting stuff. Mathematicians are starting to finally take quantum field theory really seriously. They're starting to be really good mathematicians. Sorry, this is very rude because I mean my thesis advisor was trying to make mathematical quantum field theory rigorous too. I think he was a really good mathematician. But he was working in the subject called analysis, because there's a lot of estimates and inequalities and function spaces involved in that. And there were a lot of people in analysis working on quantum field theory back in those days. And that's what I did my PhD thesis on. But when I'm talking about really good mathematicians, what I mean is that the people who have really radical creative ideas about how to reformulate quantum field theory in mathematically new ways. And there are beginning to be people who are doing that. And I suspect that because the people working on it using analysis got stuck something around the 1970s or early 1980s, that there are really new mathematical ideas needed to make progress. And so I'm glad that some of these creative mathematicians who think about algebra and topology and category theory and so on are starting to work on quantum field theory. And I think one reason why this is so important to work on is that because a lot of aspects of theoretical particle physics are sort of stuck right now, as you no doubt know, and that lots of attempts to come up with like some grand unified theory or something are not going so well right now, or string
Right.
theory or whatever. And so I hope that physicists will say like, okay, we're stuck, but look, even the stuff that we supposedly know, we don't actually know. Maybe we should think about that some more,
Mhm.
because that might have some clues, right?
Sure. So just to make it clear, so when you're saying that standard model is not mathematically consistent, you are talking about the problems that you mentioned, and you're not talking about the, the deeper problems of making quantum field theory mathematically rigorous, right? Because that's
Oh,
another
that's the
kind of
same.
problem.
No, it's well, no. Sorry. I mean, that when I say we don't know if the standard model is mathematically consistent, that to me, that's the same thing as I don't know if it's mathematically rigorous. A
Okay.
consistent theory is a theory where you can calculate and you'll never get the answer 0 = 1, right? That's what
Sure.
consistency means. So we don't know that that's true about the standard model. Why? Because we don't have any precise rules for what counts as doing a calculation in the standard model. There are lots of different things
Right.
people do to calculate in the standard model. There's like lattice gauge theory, there's different perturbative methods. When you look into lattice gauge theory, you like millions of tricks. There are all these tricks, but we don't know if all these tricks are consistent. We don't have
Okay.
any, and it shouldn't be just a pile of tricks. There should be some, there should be some theory that you can write down in a few pages and say, this is the theory. So because we don't even know if it's what the theory actually is, then therefore, when we run into these, well, you could say, you could take this attitude. You could say, like, yeah, no one knows how to make it consistent, but come on, it's got to be consistent. It works so well, it's consistent. That's like a typical physicist answer, like, come on, you can't believe it's inconsistent. We could have said that about the four color theorem too, right? We're like, why bother proving it? No one's ever come up with a map where you need 5 colors. But the idea of trying to do things rigorously is that you don't just like accept it, like, because it's
Yeah.
worked so far, it's gonna keep working. So, so,
Yes.
but okay, but the fact is that even within this attitude of like, come on, it's probably consistent, there are people finding problems in the standard model, like this, that the Higgs might destabilize the vacuum. That's good as far as I'm concerned, because that means that like it makes even the so-called practical people realize that there are open questions, fundamental questions connected to the standard model. But
Sure.
for me, even if it looked like it was working fine, I would still be very annoyed at the fact that no one has ever proved that it works.
Mhm. Well, I actually mentioned this thing because the rigor thing is not special to standard model, right? It's
No,
it's the problem for any interacting quantum field theory in 4 dimensions, like because of Hawk's theorem and things like that. So, are you gonna get rid of that just by studying standard model, or or you have to talk about the problem of interacting quantum field theories in 4 dimensions as
I
a
mean, you
general
definitely need
problem?
to understand them in general.
Mhm.
Um, the Probably the best way to prove that the standard model makes sense is to prove it as part of a general theory of how 4D quantum field theories work. Right now, it's just a complete bunch of folklore and belief. So, for example, people believe that QED is not consistent because they believe that there's a Landau pole, uh, which is which means that when you try to extrapolate QED to very, very ridiculously short distance scales, much smaller than the Planck length, that the running coupling constant that measures the strength of basically like the fine structure constant goes to infinity. And they
Yes.
believe that that means that the theory is inconsistent. But all that's just hand wavy stuff. It's approximate calculations. They know are approximate. They don't have any proof that a Landau pole is a is a killer. So yeah, so it's not just the standard model. It's like the whole subject is needs better understanding, and that's great, great thing to work on. It's hard. It's a hard problem. That's why people don't work on it, because they work on it for a while and say like, ugh, this is too hard. And so they do something easier. But so it may be that only mathematicians will work on it. I mean, the good thing about mathematicians is that they never give up, okay? Get this guy with Fermat who writes in the margins of his book, yeah, I think this is true. I think I proved it. And he never shows us the proof. We work and work and work and work. Then along comes people who come up with the Taniyama-Shimura conjecture. It's like an amazing conjecture about elliptic curves. Then this guy Frey shows that if you could prove that conjecture, then you could, Fermat's last theorem will follow. Then all of a sudden, this Fermat's last theorem stops being some stupid little puzzle about x to the n plus y to the n equals z to the n, and it becomes part of an actual interesting mathematical problem about geometry of elliptic curves. Then Wiles locks himself up, I'm exaggerating, locks himself up in an attic for 2 years. He thinks he proves it. Then they discover his proof has a flaw. He's sweating bullets. He works with a grad student to fix the proof. That's the kind of thing that you need to really solve a problem that took hundreds of years. So this problem about the standard model, it might be that hard.
Actually, my last question before I go to the people's questions is a bit related to what you just said. So it's a very good time to bring it up. So what advice would you give to younger researchers regarding dealing with failure in research?
Yeah. So first advice, don't start trying to prove a famous open conjecture. Okay. Just like a terrible thing to do. Wiles had tenure at Princeton when he did this. So then is the time to start trying to do like impossible tasks, like proving Fermat's last theorem. So no, when you to deal with failure, I mean, the best way to deal with failure is to not fail, right? Isn't that the best way to deal with failure? So how do you not fail? So I discovered that whenever I tried to prove something and I didn't know that it was true, I would fail. So I realized that I should only try to prove things that I know are true. And so how do you get anywhere that? Let's see, were you talking about dealing with failure for mathematicians or for physicists or
I mean,
general?
there may be some general principles, but yeah, I mean, for specific advices, you can go to mathematicians or physicists. But for example, if there is a PhD student who was doing a project, and it turned out that the project is a dead end, so it
Okay,
seems a failure, right?
okay. Yeah, so it's too late to take my first advice, which is to not fail. Okay, so you already failed. Okay, so what's so I got to give you some backup advice. So the big question then really is like, um, how can you, first of all, how can you extract something useful out of your apparent failure? Very often, what happens if you're doing if you're doing theoretical work, so experimental physics, I don't have much advice for, I guess, because I don't know enough about it. But for theoretical work, one important thing to learn is that like if you, it's probably true in experiment too. If you think you've failed, very often you've done some stuff, but it just didn't add up to equal the thing you were trying to get.
Hmm.
Very important thing to do is to take that stuff that you've got and see what else you can do with it. See if there's something else you can do with it. And then you can get some success out of your apparent failure. This is especially true if you've been proceeding in an intelligent way. To solve a problem in an intelligent way, you do it in a way that if you fail, it's not just like, oh, either it completely works or it's like completely baloney. Because if you're working in an intelligent way, you're stacking bricks on top of bricks, And if the bricks don't get up to the point you want, at least you got something, right? So I mean, that's some advice before you fail, is to like work in an intelligent way so that there are like sub goals that are interesting. And so hopefully if you when you fail, there's still something there that you can do something else with. And I'll say, by the way, that Knuth has some very good advice, which is that, by the way, even if you succeed, there's something that people often forget to do. If you succeed, it means that you've built up a bunch of methods of doing something. And you should not quit when you should succeed. You should think about those methods and see what else you can do with them. So the way he says it is like if you climb up onto a mountain peak, you should look around at the other mountains that are very nearby. Now that you're way up there, maybe it's easy to go and get to some other mountain peaks too. So whether you succeed or fail to get to this peak, right, you should look for other peaks. That's one thing. I think there are a lot of other pieces of advice. I
Yeah.
mean, there's a lot of pieces of advice to be had about like how to have the psychological resilience to survive the pain of failure. That's a very important thing. That's a very important thing to have, and it may be hard to transmit the
Hmm.
information about how you have that
Yeah.
quality. I can't necessarily tell someone how to be resilient. One way to be resilient, for example, is to be working on a couple of things at once. When you're young, you may have like a thesis you're working on or a few projects you're working on, and you don't have a lot of things you're working on, maybe. Then you are very fragile because if your one thing that you're working on breaks, you go, oh no, nothing is working. When you're What you have to do though is to keep building up a bunch of things that you've thought about for a while and keep them in a notebook somewhere or in the back of your mind and don't forget them. And and as you get older, as a researcher, if you're good, you have a whole bunch of these things lined up in your desk or in your mind. And so what happens with me is like if I'm doing something and it fails, I go, oh, I'll just switch right over to the next one. I've got lots of them. And so nobody on the outside notices that like maybe 50% of the time I'm failing because I'm still succeeding enough. And Feynman said the same thing. He said like the way that you look successful is you just like had to have a bunch of things to do and a bunch of tricks you use and you just keep trying them. And then every so often something works. Every so often it works. And that's enough. That's all you need.
I see. Okay. So there are some questions from the people. I think there are like I had a lot of questions actually. I had to filter some of the questions out. Otherwise, it would have taken a long time.
Uh-huh.
So
Great.
one question is that do you believe beauty is a reliable guide in theoretical physics, or are we just chasing shadows in Plato's cave, mistaking elegance for the truth?
Uh, it's a very hard question because I think it all depends on who's we. I think some people's idea of beauty is wrong. Okay, so I think there are lots of people who think their theory is beautiful and it's not. So I think if you want a short answer to the question, I think it's that. For example, I think a beautiful theory of physics, it has to it has to it has to match, it has to be in agreement with as many of the fundamental principles of physics that we've learned over the centuries as possible. If it's just mathematically beautiful, but it does not comport with all these principles from physics that we've learned, then it could be a mathematically beautiful thing, entity, but not a good theory of physics.
Mhm.
And so then as a physicist, I would not call it a beautiful theory of physics. So for this
Okay.
reason, now I'll just annoy people. I don't think of string theory as a beautiful theory of physics. It's a beautiful mathematical entity, but not a beautiful theory of physics, in my opinion.
Sure, sure, sure.
Yeah.
Okay. I mean, not a beautiful theory of physics yet. So let's see.
Well, yes, that's
Sure.
okay.
Okay. So next
But
question
there are
is that
certain particular principles that it does not comport with that that
like
maybe
what?
someday someone will figure out how to deal with. Yes. Yeah.
Okay. Sure, sure, sure. Okay. The next question is that what math would you say is absolutely required in undergraduate in order to be competent in formal theory?
Well, theory. I never talk about formal theory. I mean like
It's a very open-ended
abstract,
question.
pure mathematics. Sorry?
Yeah.
Something
I
like
think it's a
that,
very
pure math.
open-ended question, so I didn't write that
Yeah,
down.
well, okay, yeah. So people say things like pure mathematics. Uh, I'll interpret that as meaning rigorous pure mathematics. I have a web page on my website called books.html, which is when you open it up, it says how to learn math and physics. And it goes through some topics. And that would be, I think, a way to see what I think are some of the topics and what are some of the best books for those topics. So instead of like listing a bunch of them, I would just direct you to that web page. And I will say that there are quite a few of them. It depends how good you want to be.
Mhm.
But I think, for example, if you want to be a good mathematician, well, okay, he's talking about undergraduate. So you're not going to be a good mathematician by the end of undergraduate. You'll be like ready to be a good mathematician. So you should have learned some
Mhm.
algebra, some topology, some analysis, some set theory, some real analysis, some complex analysis. I may be somewhat repeating myself, but those are rather different
Mhm.
subjects at that stage. That's a good basic bunch of combinatorics is very good. Um, Probability
Okay,
theory is very good. Some of those things.
right. Okay. So the next question is that what are some of the strategies that you use to retain the knowledge that you have gained for a long term?
That's a great question. You have to constantly work to compress your knowledge. So like when you have files on the computer and you're like running out of disk space, you can use like file compression algorithms. So similarly for the human brain, but it works quite differently. So the idea is that you don't want to remember a lot of facts. You want to remember the smallest number of facts that you need to be able to quickly get at all the other facts that you need. And that requires constant compression. The more math or physics you learn, the more you are able to forget because you realize that all sorts of things that you had to memorize before, you can now just derive or just figure out by intuition, even if you can't maybe rigorously prove them, you can just they just seem obvious to you. And so I one of the reasons that category theory is so powerful is that after you've reached a certain point in your mathematical education, which may come after you got a PhD in mathematics, actually, you realize that like to go further and learn more, you really need to get serious about compressing knowledge. You need to take whole different subjects of mathematics and crush them down to 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 see that they're like special cases of things that happen in category theory. Um, and and so
I
that's
see.
why, like when I was in my 30s and 40s, I started really getting excited about category theory. Um, and so yes, it's you can't You can't just memorize lots of stuff. It doesn't, I mean, you could for a while. Some people are better than others, but you just eventually it just runs out. It just doesn't work. It's just much better to know the key important things. And the key important things are really hard to get to. So like for me, like a really basic fundamental thing is that like you can define a monoid in a monoidal category. For me, that's like a really simple basic thing in mathematics that like if I didn't know that, I would need to know so many millions of special cases of things that it would be ridiculous. Now, this thing that I'm just mentioning here, I don't expect it to actually make sense. It's an example of something that like it only makes sense after you get there. But there are lots
Mhm.
of things like that.
I see. Okay. So the next question is that was there a math or science idea that your younger self thought was foolish, only to realize later in life it was valid?
Um, I don't, not quite. I think what there was there were subjects that I thought I didn't want to learn. That's the closest I can come to. I mean, if
Mhm.
someone told me about a math, yeah, there might have been something that I thought was foolish, but I can't remember what it is. But but I decided I was not interested in algebraic geometry. I decided like that's a branch of math that I don't want to learn. Why don't I want to learn it? Because I'm studying physics. I'm studying things like wave equations, Schrodinger equation. I need to know analysis. I need to understand functions that are in L2 spaces or differentiable functions, smooth functions, stuff like that. I don't want to just think about polynomials. That's what algebraic geometry was. What? How far could I get just thinking about polynomial functions? That's ridiculously limited function class of functions. That was my attitude. So I didn't learn algebraic geometry. Then finally, I got interested in algebraic geometry through studying geometric quantization. And I realized that all sorts of things that I had heard about in algebraic geometry that seemed pointless to me. Maybe there's an example, like ample line bundles. I was thinking, why do people care about ample line bundles? Um, Turns out like, oh, an ample line bundle is like just the right kind of thing you want when you're trying to do geometric quantization and you want a Hilbert space that's big enough. So so
Mhm.
so yes, so now I've been studying algebraic geometry a lot for the last 15 years. I started too late, but
Fine.
I'm having lots of fun.
Okay. So the next question is that you once mentioned the moving sofa problem on your Twitter page. Are there other things that fall into the category of recreational math that have also intrigued you?
Sure, that one intrigued me a lot, just enough to blog about it, but there's one that intrigued me enough to actually write a paper about it, which is called Lebesgue's universal covering problem, which, by the way, has nothing to do with the universal covers in topology, if you've ever heard about those. It's completely different. It's a simple sounding geometry problem. I don't think I'll bother to explain it. If you just type it into Google,
Mm,
you'll get an explanation of it. Simple geometry problem, like the moving sofa problem, simple to describe. When you start working on it, you discover it's incredibly hard. And I worked with a friend named Philip Gibbs and an undergraduate student named Karine Bogdasarian to try to make a little bit of progress on this problem. This problem is you're like trying to find the shape with the most area that has some property. And people have been working on it for a long time and they've been making tiny improvements, like adding 10 to the minus 18th to the area of this shape. And so we made some progress, and it was mainly Philip Gibbs who had the idea, but we wrote it up and published it. That's pretty fascinating because it's a problem that just requires knowing basically like Euclidean geometry, just really basic geometry, but it's incredibly hard.
I see. Okay, so the
It's
last question
completely
from
useless. It's a completely useless problem, but it's fun.
sure. Okay, so the last problem from the people, sorry, the last question question from the people is that so Millennium Price problem had problems had 7 problems, and one of them was Poincare conjecture that was solved. If you had to take a guess, which other problem would be solved first?
That's a fun one. Of course, it's a ridiculous question, but because nobody knows. Uh, but
But if you had to take a guess,
uh, I might I might guess this one called the Birch-Swinnerton-Dyer conjecture in algebraic
hmm,
geometry about poles of L functions of elliptic curves, because that's a subject where elliptic curves and L functions, that's a subject where people have lots of ideas. There are lots of smart people working on them, and there are lots of people making progress in that general vicinity. Yeah,
I see. So that's your guess, right?
that's my guess.
Okay.
Yeah, I also want to guess what's like the last one. So,
Okay.
like one where people have no idea what they're doing. The Riemann hypothesis is the best of the problems. That's like the
Hmm.
coolest problem, I'd say. Well, this mass gap problem is cool if you're a physicist, but if you're a pure mathematician, the Riemann hypothesis is like the most amazing problem. Uh, and what's interesting about it is that in a way nobody has a clue about how to solve it. Someone has said like in all the very difficult conjectures, there's like one part of proving it that like you're completely clueless about, and that's why you're stuck. But for the Riemann hypothesis, that part is the very first part. So they don't
Right.
even know how to start. And people are coming up with all sorts of amazing ideas, but they're all really hand wavy.
Right. I mean, do you, so a lot of people, share this opinion that you just shared that Riemann hypothesis is probably the coolest problem in maths. But their reasonings kind of differ. I mean, one reasoning that is given by the people is that if we are able to prove Riemann hypothesis, a lot of other theorems would be proven automatically. Is that your reasoning or is there some
No,
other?
no, that's not my reason. Because none of those other theorems are all that interesting. They're sort of interesting. They're like theorems about the density of primes. They're
Hmm.
all basically knowing more about the density of primes. But who cares about the density of primes? I mean, it's not, great, the density of primes. It's not all that, I mean, whoop-de-doo. So, but no, the reason why the Riemann hypothesis is so cool is quite different. So people came up with a baby version of the Riemann hypothesis, which I mentioned before. No, I didn't mention it before. Well, I didn't mention it before. It's called the Weil conjectures. And Grothendieck was working on that. And he realized it's a version that's simpler. And he realized that to solve that one, you had to understand algebraic geometry much more deeply than people had. He needed to invent a new concept of space that was good enough to work with spaces of solutions of polynomial equations over finite fields. And he
Hmm.
invented concepts like schemes. He invented Topos theory, but it wasn't really Topos theory that solved the problem. He invented new kinds of cohomology theory for schemes, like Étale cohomology. And all of this stuff is a mind-blowing because it lets us understand a much deeper connection between algebra and geometry than we had before. It's really it's you just when you learn this stuff, this is why I'm studying algebraic geometry now, because it's just so fun. You just enter this whole new world. Um, and the Riemann hypothesis is in some ways is very similar to those problems. In some ways, it's simpler because it's about the integers rather than about these fancy solutions to polynomial equations over finite fields. But in some ways, it's more complex because the kind of zeta functions that you get from these finite fields, they have just finitely many zeros and finitely many poles. And the version of the Riemann hypothesis is about like where are those zeros. But for the Riemann hypothesis, the actual Riemann zeta function coming from the integers, the usual one, has infinitely many zeros.
Yeah.
And we do not know what those zeros mean. So the reason why they and then Growth and Dieck were able, and others, and Deligne were able to solve the Weil hypotheses is they figured out what the zeros of those other zeta functions actually what they signify. They have some geometrical meaning. Right now, we do not know the meaning of the zeros of the Riemann zeta function. So to me, the fact that this simpler problem led us to this mind-blowing world of mathematics, which is like the world that algebraic geometers live in now. It's like a new world. And unfortunately, not enough of them talk about it to ordinary people because it's hard to explain. The fact that that happened suggests that when you try to solve the actual full Riemann hypothesis, it's going to be like a much better, bigger world. And we do have some clues about what that bigger world is like. There's this mystical entity called the field with one element, which is not a mathematical field in the usual sense. And we don't even know what it is. But people believe that that is like the key, might be the key to the Riemann hypothesis. So that, anyway, so basically you could say that like, if you've solved some problems that are similar to a problem that sounds simpler, and those problems led you to like completely mind-blowing this new worlds, this last one, the one that you're stuck on completely, that's probably going to be the best of all.
Right. So what you're saying is that the methods and the whole topics that you have to study in order to solve Riemann hypothesis, that's the reason for you to think that it's a
Yeah,
cool problem.
and that's the reason for most number theory problems being interesting. So
I
like
see.
all sorts of like Galois invented group theory to prove the unsolvability of the quintic, the possibility of trisecting an angle and stuff like that. It's not like we really care that much about whether you can solve a quintic with polynomial with radicals. I mean, who cares? I mean, it's good to know, but it's not like that's gonna. But what he invented was group theory, the whole idea of symmetry, and all the theorems that we use about that. So the rewards from studying number theory are always like that. They're like general concepts that are actually useful even outside number theory.
I see. So just a last question before we wrap this up. There are some other questions in number theory which are not in the Millennium Prize problems, but they are considered to be really difficult. For example, something like the Goldbach's conjecture. So do you think that those kind of problems will also give us some areas which are very interesting, like Riemann hypothesis?
Um, It's very hard. It's very hard to know. There are, by the way, a bunch of problems that aren't on the Millennium list that are very connected to the Riemann hypothesis and the Birch-Swinnerton-Dyer conjecture. There's a whole collection of open problems of the same sort connected to L functions, which are connected to these. Oh yeah, I never mentioned another amazing thing Grothendieck invented called motives. So I don't want to talk about them, but you'll hear mathematicians chatting about them. So there's a whole bunch of problems that haven't been solved that we know are like connected to really interesting them. Then there are problems like Goldbach's conjecture that are less, we don't know if they're connected to extremely interesting mathematics. Now, I should say that that's a little bit rude because this guy Helfgott has proved something called the weak Goldbach conjecture, which is a similar conjecture that's not as strong. And he developed a lot of neat methods to do it. And some of these problems, though, involve proving something sort of in an ad hoc way up to 10 to the 20. So like proof Goldbach's some kind of problem like Goldbach, prove it's true up for the first 10 to the 20th case using computers and stuff like that, and then use a systematic theory to cover the rest of the case. the
Hmm.
infinitely many other cases. So that's less beautiful, right?
Sure.
So I think right now I think that if people prove the Goldbach problem, they're going to do it in some method along those lines. And there's nice mathematics in there, but I mean, I probably don't know enough about it to be fair in my assessment of it. But it's generally considered to be less of a gold mine of beautiful mathematics. There, you may
I
have heard
see.
of this Collatz conjecture, which
Yes, I
is
was going to
yeah,
mention that.
yeah, okay, yeah. So like that's one that's like even Goldbach's conjecture, at least they're like actual number theorists like Helfgott who are making progress on similar things and
Mhm.
developing good theoretical concepts. Collatz conjecture is more like, wow, we have no idea. We just don't know anything about what to do with that. Um, and and one thing that's important to note is that using mathematical logic, you can prove that there must be infinitely many unprovable but true statements. That's a very sloppy way of putting it, by the way. Mathematical logicians never say the word true because that's a loaded word. So what I really mean is that they're like infinitely many statements that you can neither prove nor disprove. Let me just leave it at that. So if you believe in truth, then either they're true and you can't prove it, or they're false and you can't disprove it. Okay, there's a lot to say about that, but you didn't want to know about that. And but there's got to be infinitely many unsolvable math problems, and it could well be that it could be that the Collatz conjecture is one, or it could be that you can make up infinitely many Collatz-like conjectures, right? The
Yes.
Collatz conjecture is this sort of 3x plus 1 divided by 2. You could like make up others where it's like, oh, 7x plus 3, or else you do this. You can just
Yeah.
imagine, like, right, making some infinite list of them. And then you like find that a bunch of them, it seems like they always stop and some they don't. And you could like crank out Collatz-like conjectures as for your life, right? And so it could be that like infinitely many of those they're true, but there's not any good reason for them to be true. They're just sort of true by
Hmm.
chance. Um,
I see.
and yeah, so then those will be stuck, and unfortunately for those, you basically got to call the mathematical logicians in to start discussing that whole
Sure.
issue. Yeah.
So do you know? So one last thing. So do you know that before Fermat's last theorem was proven, did people used to believe that this may be one of the improbable statements?
um, I never I never heard anybody say that too much. Mathematical logicians have proved this. They have proved that you can write down certain Diophantine equations, that is, equations like 3x to the 9 plus 4xy cubed plus 7z equals 9, where you're looking for integer solutions.
Hmm.
So there are Diophantine equations that you can actually write down, and you can look them up on Wikipedia, where it's impossible to prove whether they have or don't have solutions using ZFC.
Oh, really?
Yes, so that's a
Interesting.
beautiful and sort of terrifying result in mathematical
Yeah.
logic. It's called the Matyasevich theorem, maybe. It's actually proved by lots of people, so I should list a whole bunch of names, but
Hmm.
Matyasevich is one. Um, so yes, and people are looking for the smallest one. The one they found is really complicated looking. Um, they are looking to try to find the smallest one that's unsolvable.
I see. Okay, so my questions are over. Thank you so much for your time.
Okay,
I think
sure.
I've taken a lot of your time, so thank you so much for your time, and I hope that we
Oh,
can
it's fun.
talk sometime in the
Sure,
future as
great.
well.
It was a lot of fun. I'd be
Thank you.
glad to do it again. Yeah. Bye.
No problem. Yeah, bye.
Yeah.
So if you like this video, give it a thumbs up and consider subscribing, and the YouTube algorithm thinks that you will also like this video.